So the next part of the discussion is the chapter which we are going to discuss is periodic table. Also we call it as periodic classification. If you go to the periodic table, what are the important points where we could classify? Actually, if you go for a periodic table, if you are going for a periodic table, this periodic table is broadly classified into periods, and it is also classified into groups, Groups are called columns. These groups we call it as columns. Groups are columns and periods are rows. Called rows. So here we have 7 periods. Periods are 7 and groups are 18. 18 vertical columns, 7 horizontal rows. So when you go for if you go for 7 periods, in the 7 periods what we can say is first one is shortest with only 2 elements, hydrogen and that is helium. Second, if you take second is a short period which we have the 8 elements. Total we have 8 elements. Here we have only 2 elements, here we have 8 elements, starting with the lithium and it ends with that is neon. Third, again short period. Here it starts with the hydrogen, lithium, sodium. Starts with sodium and ends with argon. Fourth, long, potassium. It ends with krypton. Fifth, again long, hydrogen, lithium, sodium, potassium, rubidium. Starts with rubidium and it ends with xenon. Sixth is the longest. Hydrogen, lithium, sodium, potassium, rubidium, and that is cesium. And here neon, argon, krypton, xenon, and this is radon. Longest period. And of course 7th is incomplete, and because it is incomplete, hydrogen, lithium, sodium, potassium, rubidium, cesium, and last one is francium. It's an incomplete period. All this comes under the groups, all this comes under the periods. You find that the first period is shortest, second and third are short, second and third are short periods, fourth and fifth are long periods, and sixth is the longest period, and seventh is the incomplete period, which we have to notice. And you are finding that every period in a period the starting element they belong to alkali metals, bending elements belongs to noble gases, ending elements belongs to noble gases. You can notice that because this is helium, neon, argon, krypton. Next one is xenon and radon. You can notice that every period is ending with a noble gas and it is starting with a alkali metal. So if you go for groups, there are total 18 groups are there. In these 18 groups, you can find that these groups are again, let me say, they are classified into blocks. Groups are classified into blocks. Blocks are classified into 4 subtypes: S block elements, P block elements, D block, and also F block elements. Again, S and P block, S block and P block together, we call them as representative. We call them as representative elements. D and F block, D block elements are otherwise called transition elements, and F block elements are inner transition elements. And D block elements are called transition elements, and F block elements are called inner transition elements. If you go for S block, again this representative elements. If you go for these representative elements, particularly in this S block, you have 1A alkali metals, and 2A alkaline earth metals, alkaline earth metals. Likewise, if you go for P block, if you are going for a P block, then you are finding that P block is made up of 13th group. Also they are made up of 13th group, 14th group, also made up of 15th, group, then also they are made up of 16th group, also they are made up of 17th group. 13th group we call it as boron family. 13th group we call it as boron family. 14th group carbon family. 15th group we can call it as nicogens. Nicogens. 16th group you can take oxygen family. And 17th you can take it as halogens, and 17th you can take halogens. 18th group if you take, these are noble gases. Yeah, 15th group nicogens, 14th group carbon family, and 13th group that is boron family, and 18th group we can call it as noble gases. and so on and so forth. So if you look into the design of the periodic table, what you are noticing here is the periodic table more or less looks like this. That is, let me put it in this way: hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Then beryllium, magnesium, calcium, strontium, barium and radium. Then scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. If you take, then we can take here, this is potassium is 19 atomic number, calcium 20, 21 scandium, 22 titanium, 23 vanadium, 24 chromium, 25 manganese, 26 iron, 27 cobalt, 28 nickel, 29 copper, 30 zinc, 31 is gallium, 32 is germanium, 33 is arsenic, 34 is selenium and 35 I think it's going to be, that is bromine. 35 is going to be bromine. So what we are noticing over here is like in particular rubidium 37, strontium 38 and cesium 55 and barium is 56. This is 55 plus 32, 87 and this is going to be 88, 11, 12, 11 atomic number, 12 atomic 3, 4 and this is 1. So what we are just trying to understand here is very simple method. Practice always makes you perfect. Practice always makes you perfect in remembering the elements in the periodic table. So here if I just draw a horizontal line like this, and if I cut off the one more horizontal line like this, then I can say that all this comes under, that is P block, this comes under S block, this comes under S block, all this comes under S block, this comes under D block and this comes under, that is P block. Here of course if you go for the beryllium, lithium beryllium, then boron aluminum, I think here I can take boron, here I can take here boron and this is aluminum. Likewise again I can take carbon, silicon, germanium, I can take nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, fluorine, chlorine, bromine, boron, aluminum, gallium, indium and thallium, carbon, silicon, germanium, tin and lead, nitrogen, phosphorus, arsenic, antimony and bismuth, oxygen, sulfur, selenium, tellurium and polonium, fluorine, chlorine, bromine, this is bromine, fluorine, chlorine, bromine, iodine and astatine. All this comes under, that is, this comes under P block. This is P block. And here boron atomic number is 5, 13, 31, 31 plus 18, 49, 49 plus 18, the 49 plus 32, 81, carbon atomic number 6, silicon 14, germanium 32, 10, 50, this is 82, 7, 15, 33, 33 plus 18, 33 plus 18, I think it is 51, and this is going to be 83. Oxygen atomic number is 8, sulfur 16, selenium 34, tellurium 52 and polonium 84. Fluorine atomic number 9, chlorine 17, bromine 35, iodine 53, astatine 85, and so on. This comes under the P block. So likewise, if I am joining this order in the same pattern, in the same fashion, you are finding that here yeah, so scandium 38 is strontium, 39 is yttrium, 40 zirconium, 41 niobium, 42 molybdenum, 43 technetium, 44 ruthenium, 45 rhodium, 46 palladium, 47 silver, 48 cadmium. Here, so here you are going to get zinc, cadmium, mercury. Mercury is 80, copper, silver, gold. Gold is Au 79, nickel, palladium, platinum 78. Then cobalt, rhodium 77 is iridium. Then iron, ruthenium, osmium 76, 75 I think it is rhenium. Then here 56, 57 is 57 lanthanum, 72 hafnium, 73 tantalum, and 74 I think it is tungsten. So similarly here also what we are noticing is 89 is actinium, 104 rutherfordium, 105 dubnium, and so on. So it's an incomplete period, and so on. So what is happening here is like 75 so it's 44 ruthenium, 45 rhodium, 46 palladium, 75 rhenium. Yeah, I think so. This is D block, and what you're finding is like this is, as I told you, this is 1A group alkali metals, 2A group alkaline earth metals, and this is 3A group boron family, 4A group carbon family, 5A group nitrogen family, 6A group oxygen family, 7A group halogens. And this is 1B, and this is 2B, and this is 3B, 4B, 5B, 6B, this 6B, and this is 7B, 6B, 7B, and this is together 8B, and I call this as 8B, I call this as transition triads. I call this as transition triads. The most electropositive element, most electropositive element is cesium. Then the lightest element is hydrogen. Zinc, cadmium and mercury. These are and mercury is the only metal. It's a liquid metal. Mercury is the liquid metal. Bromine, if you take bromine, liquid non-metal. Liquid non-metal. These three elements, liquid metal, and 2b, these are called typical transition elements. Typical transition elements. 1b, if you take, these are noble metals. 1b, noble metals. Sodium and potassium, sodium and potassium, if you take particularly potassium and rubidium and cesium, these three metals, potassium, rubidium, cesium, they are used in photoelectric cells. S block elements are metals dominated. P block elements are both metals and non-metals. If you take D block elements, if you take in particular D block, they are made up of both, they are metallic, also they are amphoteric. They are metallic as well as they are also amphoteric. They are also amphoteric. And these are typical transition metals. And tungsten, this is called tungsten, otherwise wolfram, is used as a filament in electrical bulbs. And so on and so forth. This is a complete picture. And F block elements, let me finish off F block elements also. If you take F block elements, you can see a break here. 57 is lanthanum. I'm just highlighting here. 57 is lanthanum. 89 is actinium. 104 is rutherfordium. So you can see a big break in between this two set of elements. So you can take, that is 58 cerium to 71 lutetium, and 103 lavranthium, 103, sorry, this is 90 thorium, 90 thorium to 103 lavranthium. This comes under F block elements. 103 lavranthium, 90 thorium to 103 lavranthium, and 58 cerium to 71 lutetium comes under F block element. So the next part of our discussion in the periodic table is let us discuss something about the various contributions made for the development of periodic table. And before that, in the previous class, I've given you a detailed description of how the periodic table looks, and this periodic table, how we have classified them into blocks, and how we could able to separate the different blocks of elements of the periodic table into S block, P block, D block, and F block. Also the discussion went on. Now we enter into the contributions for the development of periodic table. That is, let us begin our discussion with, I'll put it like this, contributions of development of periodic table. I would like to highlight the first contribution, that is law of triads, which is given by the J.W. Duberner, law of octaves, given by John Newland. Third one, Mendeleev's periodic table, given by, that is, Mendeleev. Fourth one, that is Moseley's periodic table, if we take, okay, based on the Moseley. Fifth one, modern periodic table, given by Niels Bohr. So all these are the various contributions for the development of periodic table. In this law of triads, law of octaves, Mendeleev's periodic table, Moseley's periodic table, and modern periodic table. Here in this, the periodic property is the, that is, average arithmetic mean. Here the periodic property in J.W. Duberner's law of triads, that is, periodic property is average arithmetic mean, and we go for law of octaves. It was proposed by John Newland, and the periodic property, according to the periodic property for law of octaves, it is octave of music. Octave of music is a periodic property. For Mendeleev's periodic table, periodic property is atomic weights, and for Moseley's periodic table, the periodic property is the atomic numbers, and for modern periodic table, the periodic property is electronic configuration. So based on this, we would like to have a detailed discussion about each and every concept here in the periodic table. So one by one, let us have a discussion about this different contributions and different theories for the development of periodic table. Let us have a detailed discussion for this, and let us start with law of triads. So let's start our discussion with the law of triads. That is, number one, law of triads. It states that significance, the atomic weight of middle element is average arithmetic mean of other two elements of same group is law of triads. That means we are calculating the atomic weight of the middle element, which should be equal to the average arithmetic mean of the other two elements belonging to the same group. Suppose for example you take 1A group. 1A group is alkali metals. So I am taking here, that is lithium. We have hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. So I am taking lithium, sodium and potassium belonging to the same group. So you take lithium, you take lithium atomic weight. Lithium, if you take lithium atomic weight is 7, sodium atomic weight is X, of course atomic number of lithium is 3, potassium atomic weight is 39 and atomic number is 19, sodium atomic number is 11. So if you want to calculate the atomic weight of the sodium, X is equal to 7 plus 39 divided by 2, which is equal to 46 by 2, which is equal to 23. Here 23, therefore X is the atomic weight of sodium, average atomic weight of sodium, which is equal to 23. Like this you can take even one more example. I will take example 2 if you want, that is iodine. If you take, that is halogens, you take halogens, fluorine, chlorine, bromine and iodine, of course astatine. So I am taking here chlorine, bromine and iodine. So chlorine atomic weight is 35.5, atomic number 17, bromine is X, 35 atomic number, and iodine 53 and it is 127. So X is equal to 35.5 plus 127 divided by 2. So 127 of 35.5. So this is 5 decimal, this is 12, 156, 162. 162 means this is going to become 162.5. So X is going to become 162.5 divided by 2. This is 81.25 is the atomic weight, is the average atomic weight of bromine. So this is how we can calculate the average atomic weight of the middle element of the three elements, triads of the elements which are picked up from the same group. If you want to calculate the atomic weight of the middle element, we can calculate in this procedure. So here in the alkali metals, if you pick the triads, lithium, sodium, potassium, the sodium is going to become the average atomic weight element, which is in the middle. Its atomic weight after calculation is 23. Similarly, among halogens, fluorine, chlorine, bromine, iodine and astatine, we are picking three elements, chlorine, bromine and iodine. Here bromine is the middle element, so bromine is equal to the atomic weight of the average atomic weight mean of the other two elements. So 35.5 plus 127 divided by 2. After simplification, it's going to be 81.25. So actually, numerically, when you are calculating the atomic weight of bromine, it is 80. But because we are saying average atomic weight, it is accurately, the value is very close to 80. That is 1.25 times 1.25 value. Extra is, it's extra compared to the original value. But then this is how we calculate the average atomic weight of the given elements from the triads of the same group. So the next part of the discussion is, that is law of octaves. So if you go for law of octaves, as it was proposed by John Newland. So if you're taking the set of elements like let's begin with the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Similarly, if you go for that is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. and argon. Of course, you can take even next element, that is potassium and calcium. If you take, what you're noticing is this is 1A group, this is 2A group, 2A, and of course this is 3A, this is 4A, this is 5A, 6A, 7A, and 8A group. What is interesting here is, what we have to note here is, noble gases are not included in properties of elements. Noble gases are not included in properties of elements. Then octaves, law of octaves is not applicable. Okay, law is not applicable. Beyond calcium. Law is not applicable beyond calcium. Then if that is the case, because noble gases are not included, so I am striking off the noble gases and I am starting with the lithium atomic number 3, 4, 5, 6, 7, 8 and 9. For 9, again you take here 11, 12, 13, 14, 15, 16, 17, and this is 18. So 1, 2, 3, 4, 5, 6, 7 is the 8th element. If you count the elements 1, 2, 3, 4, 5, 6, 7, 7th, the 8th element is sodium here. So lithium and sodium, if you take the atomic number differences, the difference of 3 and 11, that is 11 minus 3 is equal to 8. Again here also, again here if you take potassium is 19, potassium atomic number is 19. So if you take 19 minus 11, which is equal to 8. So this 8 is octave of music. So therefore we can just take this number 8 is nothing but octave of music. So if the elements are arranged, if the elements arranged in increasing order, upward arrow represents increasing order. Elements arranged in increasing order, upward arrow indicates increasing order. Elements arranged in increasing order of their atomic numbers. The 8th element starting from the first. 8th element starting from first element is in octave, octave of music, atomic number, and this is element. So this is the statement which is given by law of octaves, and it is applicable only, it is the cutoff, it is not applicable. Calcium is not applicable in the law of octaves, and noble gas also they are not applicable in the law of octaves. So from this law of octaves we can understand that the first starting element and the ending element, set of 8 elements are there, 1, 2, 3, 4, 5, 6, 7 and 8th element. Again 1, 2, 3, 4, 5, 6, 7 and 8. The 8th element and the first element are always in the octave of music, and it is the difference you are finding that the 8, their atomic numbers difference is 8, and this is how the law of octaves can be understood in terms of octave of music. So this is law of octaves. So the next part of the discussion is, that is Mendeleev's periodic table. So here periodic property, atomic weights, atomic weight. So all the physical and chemical properties, all the physical and chemical properties of elements, all the physical and chemical properties of the elements are periodic functions of their all the physical and chemical properties are the all the physical and chemical properties of the elements are the periodic functions of their atomic weights. So Mendeleev has taken the atomic weights into consideration while placing the different elements in the periodic table. In fact, if you go for Mendeleev, the short form of periodic table, PT, stands for periodic table. It contains 6 periods and 8 groups. In fact, this is short form of periodic table. Long form of periodic table according to Mendeleev, long form of periodic table contains that is 7 periods and 18 groups. 7 periods and 18 groups. However, there are some limitations. in the periodic table. If you go for the limitations of periodic table, if you take limitations, no exact position for hydrogen in periodic table. Second, no place for isotopes. No place for isotopes, and also atomic weights of elements, position was irregular. That is, anomalous pairs ambiguity was not explained significantly. One example I would like to give you: if you take potassium, if you are taking potassium, that is, for example, let me put it in this way, that is lithium, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Again, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. And next is, that is potassium. Potassium is 19, atomic weight 39, argon 18, it is 40. So you are finding that this set of elements, they belong to second period, and this set of elements, they belong to third period, and you are finding that potassium belongs to fourth period. But what is interesting here is 18 argon 40 and 19 potassium 39. Because the atomic weight of argon is 40, it is supposed to be placed in the position of potassium. Because the argon atomic weight is 40, because the argon atomic weight is 40 and potassium atomic weight is 39, the potassium should occupy the argon position. The potassium should occupy the argon position, and the argon should occupy the potassium position. But in the periodic table, you find that their places have been exchanged. And of course, there is a justification saying that argon is placed below the neon in the periodic table just because argon and neon, both of them are noble gases. So they will have some reactionality in the chemical properties. Might be it is because of that reason the argon would have been placed below nitrogen. But if you take exactly according to the definition of the Mendeleev's periodic table, definitely potassium will occupy the position of argon, and argon will occupy the potassium, and argon will occupy the position of the potassium in the periodic table, and potassium will occupy the position of argon in the periodic table. So that's why this pair of I can say that 19 potassium 39 comma 18 argon 40 are anomalous pairs. Such anomalous pairs were not properly explained by the Mendeleev's periodic table, were not properly justified by the Mendeleev's periodic table. So next part of discussion is Moseley's periodic table. So here periodic property. The periodic property according to the Moseley's periodic table is atomic numbers. You know very well that atomic number of an element, is given by the symbol Z, and it actually represents the number of protons present in the nucleus of atom, and apart from this, if you go for the significance, that is significance or the statement significance, if you take all the physical and chemical properties, all the physical and chemical properties are the periodic functions. All the physical and chemical properties are the periodic functions of their atomic numbers. In fact, Moseley's experiment with the X-rays has given the expression mu bar is equal to under root of mu is equal to A of Z minus B. This is the mathematical expression where mu is the frequency of X-rays, and Z is the atomic number of element, and A comma B are the physical constants of element. Physical constants of the element. So the next part of the discussion is modern periodic table. Next part of the discussion is modern periodic table. In this, the periodic property, if I take, the discussion goes on periodic property. Periodic property. If you take, that is electronic configuration, EC, electronic configuration. What is EC here? This is the electronic configuration of elements. Electronic configuration of the elements. Next, what is the significance? Same definition almost. Significance: all the physical and chemical properties of elements. The elements are the periodic functions of their periodic functions of their electronic configuration. All the physical and chemical properties are the periodic functions of the elements are the periodic functions of their electronic configuration. So in this modern periodic table, we would like to have few more points under discussion. And this modern periodic table was actually proposed by Niels Bohr. It was proposed by Niels Bohr. So let's continue the next part of the discussion in the modern periodic table. Conclusions. Let me put it in this way. Conclusions of modern periodic table. Conclusions of modern periodic table. Let me put it in this way. According to the modern periodic table is made of 18 groups, also called columns, and 7 periods, which we also call them as rows. Next, each group or period contains elements contains valency electrons. Again, in a group, every new element, let me put it in this way, for every new element, a new shell is added. For every new element, a new shell is added. For every new element, a new shell is added. For example, if I am take one example to justify. I am taking 1A group, alkali metals, take lithium, atomic number 3, nucleus, first shell 2 electrons, second shell 1 electron. Go for sodium, atomic number 11, nucleus, first shell 2 electrons, second shell 8 electrons, and next shell 1 electron. If you go for potassium, 19 atomic number, so nucleus, first shell 2 electrons, second shell 8 electrons, third shell again 8 electrons, fourth shell 1 electron, and so on and so forth. And mind you, this lithium, sodium and potassium, they belong to the same group. Lithium belongs to 1A group, sodium belongs to 1A group, and potassium also belongs to 1A group. Don't forget that. But however, if you go for in a period for every new element, only a new electron is added. For example, take one example. In a group, for every new element, a new shell is added, we are saying. Again, in a period, we are saying for every new element, only a new electron is added. How come? Take one example. If you take an example, suppose I am taking for second period elements. If I am taking second period elements in the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, say for example. These are all the elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Lithium atomic number 3. Lithium atomic number is 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9 atomic number, and neon it is 10. So if you take particularly lithium nucleus, first orbit 2 electrons, second orbit 1 electron, only 2 shells. Again beryllium, if you take 2 electrons and 2 electrons, 2 electrons and 2 electrons. So you are finding that for every new element, only a new electron is being added. Again 5 electrons in the valency shell, nucleus 2 electrons, 4 electrons. Again nitrogen 2 electrons, 5 electrons. Again nitrogen 2 electrons, 6 electrons. Again fluorine 2 electrons, 7 electrons, 2 electrons, 8 electrons, so on and so forth. So the next part of the discussion in the modern periodic table is continuation. That is, if we take common distribution of electrons into various shells. So here if you take let us take a nucleus. This is nucleus, this is first shell, this is second shell, this is third shell, this is fourth shell, this is fifth shell, this is sixth shell, and so on and so forth. In general, first shell is always 2 electrons, second shell 8 electrons, third again 8, 18 electrons, 32 electrons. So here this is K, L, M, N, O, P, 1, 2, 3, 4, 5 and 6. The shells can be designated through any method. Either you can designate them through numericals or you can designate them through alphabets. You can see that this is the nucleus of an atom, of an element. These are the shells, and this is the accommodation, the capacity. This is nothing but the capacity or accommodation of electrons. So likewise, we can also take here from in the same diagram, we can also introduce orbitals. S orbital, S and P orbital, S, P sp and d orbital. Here you can take again sp, pd and f orbital, again s p d, again f orbital, and so on and so forth. So here s comma p comma d, all these s comma p comma d comma f are orbitals of sublevel, orbitals of a sublevel. So therefore maximum number of electrons to be accommodated in a given shell, is equal to 2n square, 2 into n square. So here if n is equal to 1, then 2 into 1 square is equal to 2 electrons. That means the first shell can accommodate 2 electrons. If n is equal to 2, 2 into 2 square, so total 8 electrons, and so on. So this is the accommodation of electrons into various shells or various energy levels. So the next part of the discussion is periodic trends in periodic table. Periodic trends in periodic table. We are supposed to discuss about the valency. We are supposed to discuss about the atomic size. Supposed to discuss about the metallic nature. Supposed to discuss about the non-metallic nature. So valency, atomic size, metallic nature, and non-metallic nature. Frankly speaking, if you go for valency is simply the combining capacity of an element. Valency is simply the combining capacity of an element. We can call it as valency, or the net charge acquired by a given species either due to loss of electrons or gain of electrons is the oxidation state. The oxidation state can be termed as valency, and valency is simply the combining capacity of an element. If you go for the atomic size, the distance from the positively charged nucleus to the outermost orbit, where it's the nuclear attraction from the nucleus to the outermost orbit and its electron cloud is felt from the nucleus to the outermost orbit, we call it as atomic size. And metallic nature is directly proportional to the electropositive character of a metal, and non-metallic nature of a given element is directly proportional to the electronegativity of a given element. In general, all the metals, if they are metallic in nature, they have a tendency to lose electrons, and all the elements which have non-metallic in nature, they have a tendency to gain electrons. So let us justify these properties by taking suitable examples. So let's continue. If you go for valency, combining capacity of element is simply called as valency. Valency can be calculated by V for valency for elements from 1A to 4A group. For elements of 1A group to 4A group, valency is calculated by valency is equal to group number. Valency is equal to group number. Example, you can take, if you take sodium which belongs to 1A group, this sodium, its valency is equal to 1A group. If you go for magnesium, you go for aluminium, it belongs to 3rd A group, its valency is equal to 3. Group number is equal to valency. But for elements from 5th A to 8th A group, 8th A group, valency is equal to group number minus 8. Take one example. Here if you take example, you take phosphorus which belongs to 5th A. Its valency can be calculated by valency. V is calculated by, belongs to 5th A, so 5 minus 8 which is equal to minus 3. So therefore, ignoring the sign, ignoring the negative sign, you can simply say that the valency of phosphorus is 3. You go for sulfur, belongs to 6th A group, so its valency V is equal to group number minus 8, so 6 minus 8 which is equal to minus 2. So what is its valency means 2. Okay, overall valency is minus 2, simply valency is 2. So like this you can calculate the valency for the various group elements using the formula valency is equal to group number and valency is equal to group number minus 8. So these are the two concepts which you have to keep it in your mind. Then after that, if you go for second one, that is, this is the first case, number 1 valency, number 2 atomic size. So if you go for atomic size, if you take period, group, reason. Atomic size in a group decreases and in a group it increases. In a group it will increase. A, in a period atomic size decreases because in period if you take nuclear charge, the nuclear charge increases, nuclear force of attraction increases between nucleus and valency electrons. So this is something about the decrease of the atomic size in a period. This is the justification. If you go for a group, in group, that is B, in group you find that nuclear charge, of course here also nuclear charge, NC stands for nuclear charge increases, nuclear force of attraction NFA, nuclear force of attraction decreases between nucleus and valency electrons. Nuclear force of attraction decreases between nucleus and the valency electrons. Is the reason why we have to understand that the atomic radius decreases in a period and the atomic radius increases in a period. Atomic size or atomic radius both mean one and the same here. Atomic size, or you can say radius. Atomic size and atomic radius. Atomic size, and this is atomic radius and atomic size. So the next part of the discussion here is, that is metallic nature and non-metallic nature. So if you go for metallic nature, property of metals, it is the property of metals, property of non-metals. Example, you can take sodium, potassium, rubidium, cesium, manganese and so on. Non-metals, oxygen, sulfur, hydrogen, nitrogen, phosphorus, all these are non-metals. Metallic nature of metals is directly proportional to electropositive character. Nature, non-metallic nature of elements is directly proportional to electronegative nature of elements. Metallic nature, if you go for periods, decreases, and for groups it increases. Similarly, non-metallic nature in a period it increases, in a group it decreases. Upward arrow is meant for increase and downward arrow is meant for decrease in the case of the variation of the metallic and non-metallic nature. Example, left to right in a period. If you go for a period in particularly, if you go for third period, say I am taking third period, starts with the lithium, sodium, potassium, calcium, up to you can take that is potassium means it will start, or else you can take potassium, calcium, then scandium up to 31 gallium, germanium, arsenic is 50 A group family, and that is oxygen, sulfur, selenium 34, bromine 35, selenium, and finally bromine. So I can say bromine, this is a period. So bromine is a non-metal. Whereas potassium is a metal. So you can very clearly understand that in any period you find that the metallic character gradually changes to non-metallic character in a period. If you go for a group, in particular if you go for a group, any group you take, that is you take carbon family, that is carbon, silicon, germanium, tin and lead. Here lead is a metal and carbon is a non-metal. Mind you, this carbon, silicon, germanium, tin and lead, they belong to a group. In group you find that the starting element is non-metal and the last element is the metal. So that means in a group always the metallic character will increase, and in a period the metallic character will in a group the metallic character will increase, and in a period the non-metallic character will increase. So generally, so therefore from this discussion what we can do here is, that is all metals, if we take all in metallic nature, all metals, they lose electrons, they lose electrons, so they are reducing in nature, and all non-metals, they gain electrons, hence they are oxidizing in nature. They are oxidizing in nature. And moreover, here one particular point what you can highlight here is, that is increase of nuclear charge, increase of nuclear charge decreases the tendency to attract electrons, whereas here increase of nuclear charge in both the cases, in metallic character and non-metallic character, there is increase in the nuclear charge. Increase in the nuclear charge will increase the tendency to attract electrons, from the nucleus, that is, increase of nuclear charge will decrease the tendency to attract electrons by the nucleus. Therefore the metals can easily lose electrons, therefore they can lose the electrons very easily, and they can become reducing nature, they can show the reducing nature property. On the other hand, if you go for non-metallic nature of the elements, of course there is an increase in the nuclear charge, so therefore there is an increasing tendency to attract electrons by the nucleus within that element, so that it can show the gain of electrons nature, and finally it can become oxidizing nature. So let's discuss the next part of the topic in periodic table. That is, today we are going to discuss something about the exercise. Few questions we are going to discuss in the periodic table. In that, let me take one small exercise, that is exercise. If you take, that is y third period in periodic table has only 8 elements. This you can answer it. The solution for this question is, you can answer the question from according to Mueller's diagram. Based on increasing order of energy of orbitals. We can take 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and 6p. Again 7s, 5f, 5d, 4f, This is 5s 4d 5p, 6s 4f 5d, this is 5f 6d 6d, and 7p. So what you are noticing here is, like if you take, this is the first period, this corresponds to first period, this corresponds to second period, this corresponds to third period, this corresponds to fourth period, and this corresponds to fifth period, and the sixth period corresponds to 4f orbitals, and seventh period. So in the first period we have 2 electrons, which corresponds to 2 elements. In the second period it corresponds to 8 electrons with 8 elements. Third period again 8 electrons with 8 elements. Again fourth period corresponds to 18 electrons with the 18 elements. Again fifth period corresponds to 18 electrons with the 18 elements, 32 electrons with the 32 elements, and of course seventh period incomplete electrons, of course seventh period also 32 electrons, but with the incomplete elements. So what you are noticing is, in the third period, if you apply the formula, second and third period, if you carefully observe, you find that in the second period and in the third period the number of elements which are to be assigned are one and the same. This is because actually the elements are divided into, the elements are in the form of blocks. The elements, if they are blocks, suppose if I go to the orbital picture of the atom or an element, you take nucleus, first shell, second shell, third shell, fourth shell, fifth shell, and so on. This is like particularly first shell contains s orbital, second shell contains sp, third contains sp d, fourth contains sp d and f, s p d f and g. That means here we are filling 2 electrons, here we have 2, s orbital can accommodate 2 electrons, p orbital can accommodate 6 electrons, 2, 6, 10, again 2, 6, 10, 14, again 2, 6, 10, 14, and so on. So here what is happening is, this is, if this is 1, 2, 3, 4, 5, fifth shell, for first shell number of electrons are 2 electrons, next second shell 8 electrons, third shell 18 electrons, and the fourth shell fourth shell 32 electrons, and fifth shell greater than 32 electrons. Fifth shell is greater than 32 electrons. Now here we are, what we are doing is, just we are trying to take this in the form of blocks. This is second and third period contains only 8 elements. The reason is very simple, because it is a short period, and one reason it has short period, it involves only s and p orbital, a maximum of s and p orbitals, a maximum of 8 electrons can be accommodated between s and p orbital. That is why the third period elements has only 8 elements with its 8 electrons, that is 2 electrons in the s orbital and 6 electrons in the p orbital. So the next part of the question here under exercise is, we can just take, that is Second question, what are isotopes and isobars, and name two elements which have two electrons in outermost shell. So if you take isotopes and isobars, here in the case of isotopes, elements contains same atoms, elements contain different atoms. They have same atomic number but different mass number. They have different atomic number. They have different atomic number but same mass number. So here examples, you can take plenty of examples. You can take 1 hydrogen 1, 1 hydrogen 1, 1 hydrogen 2, 1 hydrogen 3. These are isotopes of hydrogen. You can also take 17 chlorine 35 and 17 chlorine 37. Similarly here also, if you take examples, yes, you can take, that is 18 argon 40 and 20 calcium 40. You can take. Also you can take, that is you can take 7 nitrogen 14, 6 carbon 14. You can see that their atomic numbers are different and their mass numbers are also different. Hence we can say they have different physical and chemical properties. Here, because they have same atomic number but different mass number, these isotopes, they have same physical and chemical properties. That is something about the isotopes and isobars. Name two elements which have two electrons in the outermost orbit. That is, you can take, if you take for second one, for third question, if you take, that is particularly third question solution. Okay, third question, you can take solution for that. You can take two electrons in the outermost orbit, means it should be elements of alkaline earth metals, like beryllium, magnesium, calcium, strontium, barium and radium. Beryllium atomic number 4, magnesium 12, calcium 20, strontium 38 and 56 plus 32, 88 is radium. So beryllium helium of 2s2, magnesium neon of 3s2, then calcium argon of 4s2, strontium krypton of 5s2, helium neon argon krypton xenon of 6s2, and radon of 7s2. So what you are noticing is general electronic configuration. General electronic configuration is equal to ns2, because it is ns2, because the configuration is ns2. Valency shell electrons is equal to 2. So this is the answer for the third question, that is number of valence electrons present in the second A group elements, alkali and earth metal. So you can take any two elements. Magnesium and calcium contains 2 electrons in the outermost orbit. If you take magnesium, for example, magnesium atomic number is 12. Take nucleus, 2 electrons in the first orbit, 8 electrons in the second orbit, and again 2 electrons in the last orbit. So these are the valency shell electrons, electron distribution, valency shell electrons, electron distribution. So next part of the question, that is fourth question. Suppose four elements A, comma B, comma C and D are given. Classify based on electron arrangement in shells, classify them into respective groups, group period and reactivity. Group and reactivity. Suppose you take A, B, C and D. This is 2, 8, 1. This is 2, 8, 2. Then this is 2, 8, 8. And this is 2, 8, 7. 4 different elements are there. So here this is nothing but electronic arrangement. Let us say this, I can just classify it like this. Element, electron distribution, then electron distribution. Here you add all the electrons, that means these are all electrons. So 2 electrons plus 8 electrons plus 1 electron, total 11 electrons. 11 electrons means it is going to be 11 means it is going to be sodium. Again 2 electrons plus 8 electrons plus 2 electrons, okay, which is going to be 12 electrons. 12 means it is magnesium. Again 2 electrons, 8 electrons, 8 electrons, means total 18 electrons, means it is argon. Again 2 electrons, 8 electrons, 7 electrons, means total 17 electrons, means it is chlorine. So that means there are 4 different elements. So here based on this what we can do is like now we can identify sodium belongs to the first group. Sodium belongs to 1A group, that is first group of periodic table, and it belongs to second period of periodic table. Again, next, if you go for magnesium, yes, magnesium belongs to 2A group, or this is magnesium, again it is first group of periodic table, again second period of periodic table. Go for chlorine, belongs to 7A, halogens, it belongs to 17th group of periodic table and it belongs to third period. Of periodic table. Last one, yeah. So chlorine we have completed. Next, argon belongs to 8th A or 0 group, 18th group of periodic table, and it belongs to, that is chlorine, argon, so it belongs to third period of periodic table. So among you can see, because sodium contains incompletely filled electrons. Sodium contains incompletely filled electrons in the valency shell, so it is chemically reactive. So here A is sodium, incompletely filled electrons in the outermost orbit, so more reactive. B, magnesium, less reactive because of stable electronic configuration. C, argon, chemically inert because of completely filled electrons, completely filled electrons, completely filled electron. The C is argon. Here it is argon. What is D? D is nothing but chlorine. So chlorine is more reactive. Because of incompletely filled electrons in the valency shell, it is more reactive, 7 electrons. So in this way we can classify them into periods, groups. And also into their more reactivity and less reactivity. In the periodic table, one thing what you have to keep in your mind is, like any element, if it is having incompletely filled electrons in the outermost orbit, that pair of elements which have incompletely filled electrons in the outermost orbit, these elements with the incompletely filled electrons, they try to participate in the chemical reaction and they become chemically reactive. But on the other hand, elements which have stable electronic configuration, which are satisfying the octet configuration or duplet configuration in the outermost orbit, such elements, they do not involve in the chemical reactions because they are already stable, so they do not participate in the chemical reaction, so therefore they are said to be chemically inert. We take the argon as chemically inert element because already in the valency shell it has 8 electrons and it is satisfying the octet stability. If you take magnesium, even if you take magnesium, it contains 2 electrons in the valency shell, still it is less reactive compared to the sodium. And if you compare it to magnesium is less reactive compared to the sodium because we need 2 times of the ionization potential energy to remove the 2 electrons from the sodium, whereas in the case of sodium we need two times ionization energy. We need 2 times of ionization energy to remove 2 electrons from the valency shell of magnesium, but whereas in the case of sodium we need only 1 time of ionization energy to remove the valence electrons from sodium. So lesser is the amount of energy required to pull the electron from the element, more is its reactivity. More is the amount of energy in the form of ionization energy, less is the reactivity. So in this way we can classify the elements into respective periods, respective groups and their respective chemical reactivity and chemical inertness.